Welcome to the Explainer. Let's just jump right in, shall we? Today, we are demystifying the invisible rules that dictate absolutely everything around us. Whether you're simply walking on a sidewalk, throwing a basketball, or literally launching rockets into deep space, there is a universal rulebook at play. And I promise, by the end of this Explainer, you're going to see the physical world in a completely new, structured way.
I mean, think about this for a second. If you roll a ball across the floor, why does it actually stop? It's this everyday mystery we totally take for granted, right? For centuries, people thought objects naturally just wanted to come to rest. But, as we're going to see, Isaac Newton's fundamental rules of motion provide the ultimate answer to this question, proving that absolutely nothing in the universe happens without a very specific, calculable reason.
So here is our roadmap for today. First, we'll cover the mystery of motion. Then, first law, mastering inertia. Second law, calculating force. Third law, action and reaction. And finally, the universe in motion.
All right, kicking things off with Section 1, the mystery of motion.
To really appreciate these rules, we kind of need to set the historical stage. Our story actually starts way back in 1665. A 23-year-old Isaac Newton, who was, believe it or not, sheltering in the countryside to avoid the bubonic plague, observed an apple falling from a tree. It's this famous, almost cinematic story, but it sparked a monumental realization about the role of the Earth's attraction. Fast forward to 1687, and Newton publishes his absolute masterpiece, the Principia. In it, he laid out his 3 empirical laws of motion, and honestly, this brilliantly illustrates the sheer power of physics. Even as we look toward the year 2026 and beyond, these exact same laws still govern our daily practical lives.
Which brings us to Section 2, first law, mastering inertia.
So, by definition, inertia is the inherent property of a body to maintain its state of rest or uniform motion unless an external force acts on it. You can basically think of it as the fundamental laziness of matter. And here is the absolute key takeaway. Mass is the measure of that laziness. The more mass something has, the more stubbornly it resists changing what it's already doing.
And that directly forms Newton's first law, which is often called the law of inertia. A body at rest will remain at rest, and a body moving with uniform velocity will just continue its motion indefinitely. It will only stop or turn or speed up if an unbalanced external force compels it to do so. So the really crucial point here is that no force is needed to continue the motion of an object. Force is only needed to change the motion. This law effectively gives us our qualitative definition of what a force actually is.
To really anchor this abstract concept, just picture your everyday experience riding on a bus. When you're standing in a bus and it suddenly starts moving forward, you fall backward, right? Why? Because of inertia. Your body was at rest, and it literally tries to stay at rest while the bus moves forward under your feet. Conversely, when the moving bus suddenly hits the brakes, you lurch forward. Your body was in uniform motion, and it just wants to keep moving forward even though the bus itself has stopped.
Moving on to Section 3, second law, calculating force.
Now that we know what force does conceptually, how do we actually calculate the force required to overcome that inertia and change an object's state? Well, this brings us to what is arguably the most famous equation in classical physics, a literal mathematical truth of the universe. F equals ma.
Breaking it down, F is the applied force measured in newtons, m is the mass of the body in kilograms, and a is the resulting acceleration. Simply put, a force applied to a body accelerates it in that exact direction. The harder you push, the faster it accelerates, but the heavier it is, the harder it pushes back. The acceleration is directly proportional to the applied force and inversely proportional to the mass.
Let's look at the cause and effect relationship here. Because acceleration is inversely proportional to mass, a really heavy mass requires a massive force just to achieve a tiny bit of acceleration. On the flip side, a light mass only requires a very small force to achieve a massive acceleration. This is exactly why you can effortlessly throw a tennis ball across a field, but applying that exact same force to a bowling ball, yeah, that'll barely get it rolling.
Now, interestingly enough, Newton originally thought about all of this in terms of momentum. Momentum, represented by p, is simply mass times velocity. Newton referred to this as the quantity of motion a body possesses. So the most general form of the second law is actually this. Force equals the time rate of change of linear momentum, or F equally delta P over delta T. Basically, this means force is directly proportional to the change in momentum and inversely proportional to the time of impact. It's an incredibly powerful way to look at the physical world.
All right, Section 4, third law, action and reaction.
Up until now, we've really just focused on single objects. But what happens when multiple objects interact in the universe? Well, it's the rule so famous it's literally become a pop culture cliché. Every action has an equal and opposite reaction. But what does that actually practically look like? Let's unpack it.
So the absolutely crucial point here is that forces in nature always, without exception, occur in pairs. A single, isolated force, completely impossible. When body A exerts a force on body B exerts an equal but opposite force right back onto body A. And here is the nuance that trips everyone up. Action and reaction never act on the same body. Because they act on two entirely different bodies, they never cancel each other out. If they acted on the same body, the net force would be zero and nothing would ever move.
Swimming brilliantly illustrates this whole concept. Think about what you're actually doing in a pool. You're pushing the water backward with your hands and feet, right? That is the action force on the water. Simultaneously, the water exerts an equal and opposite reaction force on you, pushing you forward. It's by pushing against our environment that our environment propels us.
And that brings us to Section 5, the universe in motion.
Let's pull it all together and look at the mechanics of our reality as a cohesive three-step story. Step 1. Objects are fundamentally lazy. They maintain their state of rest or uniform motion thanks to the first law of inertia. Step 2. To change that state, unbalanced forces must step in, forcing the mass to accelerate according to the second law, F equals ma. Step 3. But you can't just apply a force without a consequence. Every single force applied triggers an equal, opposite pushback in the environment thanks to the third law. Together, these three rules dictate classical mechanics.
But, to be thorough, focused learners, we also need to know the boundaries of this rulebook. Where do Newton's laws actually break down? Well, while they are absolutely perfect for our daily lives, these classical, empirical laws break down when we look at subatomic particles. They also completely fail when objects move at speeds approaching the speed of light. Furthermore, they're only strictly valid in an inertial or non-accelerating frame of reference. For the extremes of the universe, we have to rely on quantum mechanics and relativity instead.
But for absolutely everything you do today, Newton's rulebook reigns supreme. So I'll leave you with this. The next time you take a single step forward, what invisible pairs of forces are you manipulating to move your mass through the universe? Think about the push, the reaction, and the acceleration. Thanks for joining me on The Explainer, and keep questioning the mechanics of the amazing world around you.